Welcome to Chapter 15, Recursion Study Guide video. Please hit the like button, leave a comment, and subscribe to the channel. If you are unable to do that, you will need to log in. If you do not have a YouTube account, you can create one free, and it takes less than a minute. Let's get into it. 15-1, Recursive Definitions. The process of solving a problem by reducing it to smaller versions of itself is called recursion. Recursion is a very powerful way to solve certain problems for which the solution would otherwise be very complicated. Let us consider a problem that is familiar to most everyone. A recursive definition is a definition in which something is defined in terms of a smaller version of itself. In mathematics, the factorial of a non-negative integer is defined as follows. 0 factorial equals 1. N factorial equals n times, n minus 1, factorial if n is greater than 0. In this definition, 0 factorial is defined to be 1, and if n is an integer greater than 0, first we find n minus 1 factorial and then multiply it by n. To find n minus 1 factorial, we apply the definition again. If n is greater than 0, then we use equation 15-2, otherwise we use equation 15-1. Thus, for an integer n greater than 0, n factorial is defined recursively. Let us apply this definition to find 3 factorial. Here, n is 3. Because n is greater than 0, we use equation 15-2 to obtain 3 factorial equals 3 times 2 factorial. Next, we find 2 factorial. Here, n is 2. Because n is greater than 0, we use equation 15-2 to obtain 2 factorial equals 2 times 1. Now, to find 1 factorial, we again use equation 15-2 because n is greater than 0. Thus, 1 factorial equals 1 times 0 factorial. The solution in equation 15-1 is direct. That is, the right side of the equation contains no factorial notation. The solution in equation 15-2 is given in terms of a smaller version of itself. The definition of the factorial given in equations 15-1 and 15-2 is called a recursive definition. Equation 15-1 is called the base case, that is, the case for which the solution is obtained directly, and equation 15-2 is called the general case. In recursion, the current recursive call must execute completely before control goes back to the previous call. From the previous example, factorial, it is clear that 1. Every recursive definition must have one or more base cases. 2. The general case must eventually be reduced to a base case. And 3. The base case stops the recursion. The concept of recursion in computer science works similarly. Here, we talk about recursive algorithms and recursive functions. An algorithm that finds the solution to a given problem by reducing the problem to smaller versions of itself is called a recursive algorithm. The recursive algorithm must have one or more base cases, and the general solution must eventually be reduced to a base case. A recursive function in which the recursive call is the last statement executed is a tail recursive function. A function that calls itself is called a recursive function. That is, the body of the recursive function contains a statement that causes the same function to execute again before completing the current call. Recursive algorithms are implemented using recursive functions. Next, let us write the recursive function that implements the factorial function. Int fact int num, if num equals sign 0. Return 1, else return num asterisk fact num 1. Direct and indirect recursion. A function is called directly recursive if it calls itself. A function that calls another function and eventually results in the original function call is said to be indirectly recursive. For example, if function A calls function B and function B calls function A, then function A is indirectly recursive. Indirect recursion can be several layers deep. For example, suppose that function A calls function B calls function C, function C calls function D, and function D calls function A. Function A is then indirectly recursive. Indirect recursion requires the same careful analysis as direct recursion. The base cases must be identified and appropriate solutions to them must be provided. However, tracing through indirect recursion can be tedious. You must therefore exercise extra care when designing indirect recursive functions. For simplicity, the problems in this book involve only direct recursion. A recursive function in which the last statement executed is the recursive call is called a tail recursive function. The function fact is an example of a tail recursive function. In the recursive definition of the factorial function, the general case is n factorial equals n times n minus 1 factorial if n is greater than 0. Let's take a quick break. We will return after this. Infinite recursion. Figure 15-1 shows that the sequence of recursive calls eventually reached a call that made no further recursive calls. That is, the sequence of recursive calls eventually reached a base case. On the other hand, if every recursive call results in another recursive call, then the recursive function, or algorithm, is said to have infinite recursion. In theory, infinite recursion executes forever. Every call to a recursive function requires the system to allocate memory for the local variables and formal parameters. The system also saves this information so that after completing a call, control can be transferred back to the right caller. Therefore, because computer memory is finite, if you execute an infinite recursive function on a computer, the function executes until the system runs out of memory and results in an abnormal termination of the program. Recursive functions or algorithms must be carefully designed and analyzed. You must make sure that every recursive call eventually reduces to a base case. This chapter provides several examples that illustrate how to design and implement recursive algorithms. To design a recursive function, you must do the following. First, understand the problem requirements. Second, determine the limiting conditions. For example, for a list, the limiting condition is the number of elements in the list. Third, identify the base cases and provide a direct solution to each base case. Finally, identify the general cases and provide a solution to each general case in terms of smaller versions of itself. Problem solving using recursion. Examples 15-1, 15-2, and 15-3 illustrate how recursive algorithms are developed and implemented in C++ using recursive functions. In Chapter 8, we used a loop to find the largest element in an array. In this example, we use a recursive algorithm to find the largest element in an array. Consider the list given in Figure 15-2, a list with 6 elements, 5, 8, 2, 10, 9, and 4. Suppose list is the name of the array containing the list elements. Also, suppose that list of A to list of B stands for the array elements list of A plus 1, and so on, up to list of B. For example, list of 0 to list of 5 represents the array elements list of 0, list of 1, list of 2, list of 3, list of 4, and list of 5. Similarly, list of 1 to list of 5 represents the array elements list of 1, list of 2, list of 3, list of 4, and list of 5. To write a recursive algorithm to find the largest element in list, let us think in terms of recursion. The recursive function to find the largest element in an array has 3 parameters. If list is of length 1, then list has only one element, which is the largest element. Suppose the length of list is greater than 1. To find the largest element in list of A to list of B, we first find the largest element in list of a plus 1 to list of B, and then compare this largest element with list of A. That is, the largest element in list of A to list of B is given by maximum of list of A, largest of list of a plus 1 to list of B. Let's take a quick break. We will return after this. 15-2A Tower of Hanoi Analysis. Let us determine how long it would take to move all 64 disks from needle 1 to needle 3. If needle 1 contains 3 disks, then the number of moves required to move all 3 disks from needle 1 to needle 3 is 2 to the power of 3 minus 1, which equals 7. Similarly, if needle 1 contains 64 disks, then the number of moves required to move all 64 disks from needle 1 to needle 3 is 2 to the power of 64 minus 1. It would take about 500 years for a computer to execute a simulation of the Towers of Hanoi problem with 64 disks, assuming that the computer could generate 1 billion moves per second. (15-3) Recursion or iteration. In Chapter 5, we designed a program to determine a desired Fibonacci number. That program used a loop to perform the calculation. In other words, the programs in Chapter 5 used an iterative control structure to repeat a set of statements. More formally, iterative control structures use a looping structure such as while, for, or do, while, to repeat a set of statements. In example 15-2, we designed a recursive function to calculate a Fibonacci number. From the examples here, it follows that in recursion, a set of statements is repeated by having the function call itself. Moreover, a selection control structure is used to control the repeated calls in recursion. The Fibonacci recursive function has 3 return statements. Similarly, in Chapter 8, we used an iterative control structure, a for loop, to determine the largest element in a list. In this chapter, we use recursion to determine the largest element in a list. In addition, this chapter began by designing a recursive function to find the factorial of a non-negative integer. Using an iterative control structure, we can also write an algorithm to find the factorial of a non-negative integer. The only reason to give a recursive solution to a factorial problem is to illustrate how recursion works. A recursive function executes is not faster than its iterative counterpart. We thus see that there are usually 2 ways to solve a particular problem: iteration and recursion. The obvious question is which method is better, iteration or recursion? There is no simple answer. In addition to the nature of the problem, the other key factor in determining the best solution method is efficiency. Example 613 from Chapter 6, while tracing the execution of the problem, showed us that whenever a function is called, memory space for its formal parameters and automatic local variables is allocated. When the function terminates, that memory space is then deallocated. This chapter, while tracing the execution of recursive functions, also shows us that every recursive call has its own set of parameters and automatic local variables. That is, every recursive call requires the system to allocate memory space for its formal parameters and automatic local variables, and then deallocate the memory space when the function exits. Thus, there is overhead associated with executing a recursive function both in terms of memory space and computer time. Therefore, a recursive function executes more slowly than its iterative counterpart. On slower computers, especially those with limited memory space, the slow execution of a recursive function would be visible. Today's computers, however, are fast and have inexpensive memory. Therefore, the execution of a recursion function is not noticeable. Keeping the power of today's computers in mind, the choice between the 2 alternatives, iteration or recursion, depends on the nature of the problem. Of course, for problems such as mission control systems, efficiency is absolutely critical, and therefore the efficiency factor would dictate the solution method. As a general rule, if you think that an iterative solution is more obvious and easier to understand than a recursive solution, use the iterative solution, which would be more efficient. On the other hand, problems exist for which the recursive solution is more obvious or easier to construct, such as the Tower of Hanoi problem. In fact, it turns out that it is difficult to construct an iterative solution for the Tower of Hanoi problem. Keeping the power of recursion in mind, if the definition of a problem is inherently recursive, then you should consider a recursive solution. Assuming x is an integer, The remainder of x after division by 2 is called the rightmost bit. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. If you found this video useful, please hit the like button, leave a comment, and subscribe to the channel. If you are unable to do that, you will need to log in. If you do not have a YouTube account, you can create one free, and it takes less than a minute. Thanks again, and have a wonderful day.